Okay, so once we've thought about our instruments, measuring instruments, and the kind of properties associated with them, we can start to think about quantifying, so putting values to the uncertainty that we have whenever we have and take a measurement. So we're going to look at this next sort of subtopic here of absolute uncertainty, and think about the ways that we can be systematic and consistent with the way that we identify the amount of uncertainty that we associate with each of the measurements that we take. Now, but simply, there are basically three different ways that we could go about identifying the uncertainty in a measurement, and these are three ways that we need to know that we can turn to. So, three options are: one is if we've got lots of repeat measurements of a particular value, then we're going to use the spread of that data. Remember, the spread we find by half the range, so the maximum value minus the minimum value divided by 2. So that's if we've got lots of repeats of the same measurement. The other thing that we might want to think about is if we're just taking the measurement once, what's the quality of our measuring instrument? So what is the resolution or the tolerance of the measuring instrument? We talked about those two terms in the previous video. And then the third is that you might just need to take your own judgment. So, for example, if I was measuring the length of the physics lab with a tape measure, the resolution of that is a millimetre. It's got millimetre markings on it, but I'm not going to be able to measure the width of that room to the nearest millimetre. The tape measure will bow and bend a little bit. I probably haven't gone directly straight across perpendicular to the two walls. The two walls might not even be all that parallel. It's a big room, and so there's lots of other things that will kind of get in my way. So I'm going to use some judgment and knowledge about my measurement that I've taken to identify what the quality of that measurement is. And it's always best to err on the side of pessimism, really. So state that you are more uncertain than you kind of think your lower bound of uncertainty is. So we're going to talk through those three things. The first option there was when you take multiple readings. So if you take the same measurement several times, so you're timing how long it takes for a ball to drop through 2 meters, and you drop it 5 times from 2 meters, you get 5 different times. And then in order to identify what the time is, I'm going to write down as a value. I'd find the mean, and we can all find the mean, so add them all up, divide by the number of measurements. The absolute uncertainty, so this plus or minus uncertainty, is found by the spread of the data. So for the example I've got here, I've got 1.02 seconds, 1.11, so on and so forth. That gives me a mean of 1.03 seconds and a spread of 0.085 seconds, max minus min. Now, I've got to be careful here when I'm stating my value. Right, so I can't state my uncertainty value to a greater kind of precision, more decimal places, if you like, than the value. So if my mean is 1.03 and the number of significant figures I use for that is dictated by the number of significant figures that I take my measurements with. So if you look here, the data is 2 decimal places or 3 sig fig for a lot of that data. So 1.03 seconds is fine as a way to quote my mean. I wouldn't want to quote it as 1.027. And then my spread I have to round, so it's the same. It's the same precision of data. Now, it's often the case that if you take lots of repeats, you might get a dodgy looking data point. And then the question is, do we need to consider the dodgy looking data point? And one of the ways that we're going to be asked to work with an example like this, it comes up in exams fairly regularly, is looking at dot plots. And you're asked to identify whether you need to consider potential outliers from your dot plot. So a dot plot looks like this. So this is an example where I'm measuring the resistance of a fixed resistor. I've measured it multiple times, and most of the time I'm getting values around about 45, 46, 47, 48 ohms. But I've got this one rogue one down here at the bottom left hand side of 35, and the question is, can I identify that as an outlier? And you might look at it and go, yeah, obviously, but actually, what about if it was at 40? What about if it was at 41? Is that still an outlier? So where's our cutoff point? And actually, there's a rule that we use in order to identify the cutoff point. So to verify whether it's an outlier, so what we need to do is there's a couple of stages that we need to work with here. First thing is we need to ignore our potential outlier. So we're not going to take this one into account, but then we're going to work out the mean, and we're going to work out the spread. So if I were to add all these up, so 43 plus 45 plus 45 plus 46 plus 46 plus loads of 47s plus a load of 48s plus 49 plus 50 plus 50 plus 51. So each dot represents one reading. So when I did this experiment, I measured 47 8 different times, 7 different times. Can't count. Right. Then if I've got a mean of 47 and the spread of my data, excluding my potential outlier, is 4, then what I found is that my resistance is 47 plus or minus 4 ohms. So I've got a top bound of 51 ohms, a bottom bound of 43 ohms. And then the rule, when I decide whether this is an outlier or not, is that if the suspected data point is more than 2 times the spread of the data from the mean, then we consider an outlier. So 2 times the spread was 4, so max minus min is 8, 51 minus 43 is 8, and then divided by 2 is 4. So if I am 8 ohms away from my mean, then I am essentially thinking about an outlier. So 47 minus 8 is 39. So any data point that falls below 39 is an outlier. Any data point that falls above 39 is a accepted data point, so something that we will consider when we're calculating our mean. So 2 times the spread from the mean is your cutoff point. That's something that you do need to know. In this case, our suspect one is an anomaly. So that's when we take multiple measurements, mean and spread of our data. So the mean is the value that we're going to quote, the spread is our absolute uncertainty. We can use dot plots to identify whether we've got outliers or anomalies. Sometimes we just take a single measurement. So a single measurement, we're going to have to then think about the tolerance of our instrument. What's the smallest marking on the scale divisions? So let's say I've got a big fat head on this scale. This is not a big fat head, it's a jelly sweet or something or other. Anyway, I'm going to put my big fat head above that. With a digital instrument, a balance such as this, the rule that we follow is that the uncertainty is equal to the smallest change that the scale can take. So in this case, if I'm going up in every 0.1 grams, it reads 0.01 grams. 0.1 grams. So this reads 60.9 grams. I'm not wearing glasses, by the way, that's why I keep not reading stuff. So 60.9 grams here. Then the mass is 60.9 plus or minus 0.1, because it's really somewhere between 60.8 and 61.0 grams here. So the easiest way to remember it is we're going to look at the smallest scale division, small scale change. If this was a digital balance that went up in 0.2 grams, then it would be plus minus 0.2. So we've got some of those in the department. So that's digital instruments. Analog instruments are a little bit different. That's the worst place head ever, so I'm going to move this down here. So this is an ammeter. And what we usually do with these analog instruments, so instruments where we've got some scale marking that will move, and then we'll read it off as compared in position to a background markings. What we can usually do with that is say which of those background markings our measurements or our needle, in this case, is closest to. So we decide which demarcation the value is closest to. And what that means is that we kind of make a decision. Have we kind of rounded up to the nearest demarcation, or have we rounded down to the nearest demarcation? But either way, what we're saying is that our value is the value of the demarcation plus or minus half the tolerance of the instrument, so half of the spacing between those different dashes on our ammeter. So if we have a look here, the current we can say is we're reading sort of every amp here, aren't we, between 0 and 20 amps. So we can only give our value to the nearest amp, but we can say that it's plus or minus 0.5. So we've got 3.0 plus or minus 0.5 amps. That's telling us that our value, our needle, is somewhere between 2.5 and 3.5 amps, and that's true. So we're going to go to the nearest half scale division. Now, there's a little bit of a kind of confusion there, which is that occasionally some physics textbooks also treat analog instruments as they do digital instruments, so that it's plus or minus 1 scale division. And our exam will actually accept both of those, but to be technically correct, for digital, it's plus or minus 1 scale division. For analog, it's plus or minus half a scale division. We also get to the kind of complicated factor of when you do length measurements. If you think what you're doing with a length measurement, what you're doing is you're comparing two different positions. You're comparing the position of the start of the object that you're measuring the length of to the position of the end of the object that you're measuring the length of. So the example that I've just kind of pulled up here, measuring the length of a pen on a ruler, really with those position measurements, so the position of the start, we read to the nearest millimetre, right? So 1 millimetre plus or minus, or a particular value plus or minus half a millimetre. And then at the end, the position of the nib of the pen is also to the nearest millimetre. So the value plus or minus a half. And so what we're doing then is we're comparing two positions, each of which is uncertain. So here, if we have a look closely, the start position is 15.8 plus or minus 0.05 centimetres. I've done this in centimetres, or 158 plus or minus 0.5 millimetres. The end position is 30.6 plus or minus half a millimetre. So if you look at the kind of the variation between the maximum possible length, so my biggest value for the end position, my smallest value for my start position, and compare that with the minimum possible length, so the smallest value for the end position and the biggest value for the start position, then actually that's a variation of kind of a value of 14.8, and then that can vary by 0.1 centimetres, so vary by a whole millimetre. So in other words, it's a whole scale division. So when you're doing length measurements, this is a bit when we come to compounding and propagating uncertainties. When we add different values that are uncertain together, this is the kind of rule that we've got to follow. But when we're doing length measurements, we're going to do the value plus or minus a whole scale division on our ruler or on our tape measure. Again, textbooks kind of give you a bit of textbooks are not that consistent, so the exam board give you a little bit of leeway with those. You might find it easiest to imagine that it's plus or minus 1 scale division all the way through, but to be correct, digital whole scale division, analog half a scale division, length measurements back to a whole scale division again. So we've done two techniques. We've done multiple measurements. We've done using the spread in order to identify the absolute uncertainty. We've done a single measurement and using the tolerance of the instrument to identify the absolute uncertainty. And then the third one is that we're going to use knowledge of our measuring technique. And what we're saying here is that actually, although we've got a good instrument that can take some measurements very accurately, our methodology is flawed a bit. Maybe it's quite difficult to identify an exact point that we're measuring from or between. Maybe when we do the lens experiment, we've not done it yet because of COVID-19, but when we do it, we'll see that the position of the focused image is kind of subjective, so not all that easy to define accurately, specifically. So we need to give a larger degree of uncertainty to our value than the instrument kind of suggests. So as I mentioned before, we want to be overcautious in this. So some examples: measuring a large distance with tape measures. So there are some things to consider there. Can we realistically find a width of a room nearest to the nearest millimetre? Does the tape sag? Are we perfectly perpendicular? When we did the young slit experiment, measuring the spacing between those fringes, actually finding the centre of those fringes wasn't all that easy. There kind of was a gradation from bright to dark to bright to dark, bright to dark. It wasn't very distinctive where those points were exactly. With the lens experiment, again, talked about it being quite difficult to say exactly where the image was focused. And then when we did that resonance tube experiment and you moved the kind of plunger up and down that perspex tube and were looking at the size of the waveform that formed on the oscilloscope, you noticed that actually the maximums occurred across quite a broad range. And so we couldn't be accurate to a millimetre with that. So there you've just got to kind of make an estimate based on your knowledge of the practical that you did. Now, what's going to be really important is in an exam, and actually when we're doing our practicals, that we can take steps to minimise the uncertainty of our reading. So in other words, to increase hopefully the accuracy, so how close our value comes to the true value that we're trying to measure. And there are different ways that we can minimise our uncertainty. Now, when you're asked about methods to minimise uncertainties or improve the accuracy of your experiment, what those questions are asking for is, can you minimise that percentage uncertainty in a measurement? Now, we're going to do a little bit more on percentage uncertainties and look at some questions in the next video. But we should all know how to calculate percentage uncertainty. So to find the percentage uncertainty, we just do the absolute uncertainty of our measurement divided by the value, or the mean of the values if it's repeat measurements, times by 100. So if you think about this, there are two ways that we can minimise that percentage uncertainty. Look at this fraction here. So one option is to make the absolute uncertainty smaller. So change our methodology to decrease this absolute uncertainty. Or what we could do is measure a bigger value. So maybe I'm timing how long it takes for a pendulum to swing back and forth, right? And one thing I could do is hold the ball, the bottom of the pendulum out, stopwatch in the other hand, let go, press the stopwatch, watch it swing back and back at once, and then stop my stopwatch. So time how long it takes for one swing. But more accurate would be to maybe count for 10 swings and see how long that takes. And what I'm doing there is I'm increasing the value here. So my absolute uncertainty, that's to do with my reaction time, so probably to nearest hundredth or nearest tenth of a second, or 2/10 of a second, 0.1, 0.2 seconds is my absolute uncertainty. But the bigger this value is, the smaller my percentage uncertainty. We did it when we were looking at the young slit experiment, the bright dark, bright dark, bright dark. We measured across multiple fringes, and that increased our length measurement, increased the value, and we kept the same absolute uncertainty. We could decrease this absolute uncertainty, I don't know, use a better instrument, so measure the thickness of something. Where's the camera? Thickness, something about that thick. We could use a screw gauge micrometer instead of a ruler. So, to minimise, we're going to measure across multiple values and repetitions. So the absolute uncertainty will remain the same, the magnitude of the value will increase, so that decreases the percentage uncertainty. Use an instrument with greater precision, we've talked about that. So that has the effect of reducing the absolute uncertainty. And then the other thing that we can do is think of alternative measuring techniques. Are there other techniques or other instruments that we could use to improve the accuracy of our reading? So again, another experiment that we've missed due to stupid COVID-19 is looking for finding the Planck's constant from a series of different coloured LEDs. So what we were trying to do there was, we did talk about it, find the striking voltage, so the voltage at which the LED first lights up, and if we can kind of mitigate the light in the background, so use a little tube or turn the lights down in the lab, it's a lot easier to see that LED turn on. So just sort of refining our techniques. Right, so that's kind of a bit about how we can quantify, identify absolute uncertainties. You guys are going to have to be able to think about these dot plots. How can we identify outliers? Work out through these different methods of quantifying our uncertainties, so using spread and means, the spread for the uncertainty, using the tolerance of the instruments and the difference between digital, analog, and our length measurements, and then being able to suggest different methods to minimise the uncertainty. Always go back to that percentage uncertainty calculation for that. Now, you've got some questions here. There's a little bit in terms of the wording which might confuse things. Okay, so if you just have a look through, you're talking here about multimeters, reading volts to 3 decimal places. So for these, we're talking about digital meters. So think about what I said about how you identify absolute uncertainties with digital meters. The length measurement, we're going to assume the zero position is exactly known, so that only the position at the end of the object has an uncertainty. So this is a little bit like, this is about the needle pointing to the nearest scale division, so plus or minus half a scale division here. And then your judgment on human reaction time for this bottom row in the table. The wording on this question here is a little bit weird, and it's the same throughout the ISO physics questions on uncertainties. So it says that we've got here a stopwatch which is accurate to the nearest 0.1 seconds. So what that means is that it's an uncertainty of plus or minus 0.05. So that phrasing is strange. So if it's accurate to 0.1, then our value, we're confident, is good to that value, so to 0.1, so to 3 significant figures in this case. So the value falls somewhere between 23.35 and 23.45. So your plus or minus uncertainty as a value is plus or minus 0.05. And then that will follow through. If you ever see something saying it's accurate to the nearest, you need to be really careful about your significant figures. The rest of these are relatively straightforward. For this bottom one, you're given some repeat measurements, and you're also asked to kind of what happens when you add bits of string end on end as well. So you want to think about what the spread of your data is for the uncertainty, and when you've got the uncertainty of two pieces of string, the uncertainty of the total length of each of those pieces of string is the sum of those two uncertainties. Right. So that's absolute uncertainties. Next video we're going to talk about how you work with percentage uncertainties, a little bit shorter than this one, but the longer ones are to follow when we're talking about propagating uncertainties. So have a go at those other physics questions, and meet you in the next video.